welcome back, Panda lecture. It's been about 4 years. Today we're going to talk about threads, because that's what we started talking about last week, and seemed like a good thing to start up with. Lots of people like to use threads. Panda does technically support threading, but a lot of it is experimental or hypothetical at this point. So a lot of the stuff I'll be talking about is real, and a lot of the stuff I'm talking about is yet to be built. And I'll make a distinction between the two. There are, looks like most of it we got here is for programmer bent, so you probably all know about threads already. For posterity, I'll go ahead and talk a little bit about thread concepts, just to put it on the video. Threading. A thread is a lightweight process, as a common definition. It's a parallel thread of execution, code happening at the same time, and the key thing that makes it a thread as opposed to a process is that it happens in the same memory space as your other threads. So you're all accessing the same variables at the same time, potentially doing all sorts of terrible damage that way. But there's lots of good reasons to use threading, particularly as we get closer and closer to the limit of what we can do with a single processor. Moore's law is starting to run out on a single CPU, as everybody tells us, so we have to start going multiprocessor. And Intel and AMD have swallowed that pill, and they're starting to give us more and more multi-core CPUs. More and more CPUs in people's homes will have multiple CPUs, multiple cores, and we better start being able to develop to that effectively, or we will be technologically bereft. Let's see, of course, threading is difficult. All sorts of things can go wrong when you start doing threads. Most common things that people know about are race conditions. Common classic example, just incrementing a number. If two threads try to do the same number at the same time, you typically will only increment it once. And this is a real problem in things like Panda, where everything's reference counted. If you want to increment a reference count, you better be sure you increment it properly on each thread without competing with other threads at the same time. Another common problem with threads is deadlock. This is real hard to track down, but if you have two threads that try to grab a mutex to protect themselves from, say, incrementing a reference count, if they both try to grab alternating mutexes while they're each holding a different mutex, each other's mutex, then bam, either one can move and the whole process grinds to a halt. And it's easy to introduce deadlocks, it's easy to introduce race conditions, it's real hard to detect either of those, and real hard to debug either of those. So for the most part, if we introduce threading into Panda, it will be as low level in Panda as possible, try to protect the application developer from having to think about threads, just so that as few programmers as possible need to be bothered by this whole thing. But there are other things that you sometimes want to do at the high level, and I'll start talking about that. Okay. So Panda does have thread support built into it. It has to be compiled in. There are several different modes in which you can compile Panda threads. I have no whiteboard markers. Ah, thank you. I'll pick a permanent one. Let's see, first option is no threads.
Done.
Yeah, that's right. We've had this one from the beginning. And this is the way we typically compile Panda these days. This is the way Toontown runs. This is the way panda3d.org provides Panda. And there's a lot of good reasons to provide a no-threaded version of Panda. First reason is that as long as you're going to be on a single CPU, this is the fastest possible Panda you'll get. Once you start introducing threading concepts, it's going to slow everything down across the board. Other reason is that a lot of our threading stuff is still experimental, so turning it on is a little risky. So for various good reasons, the vast majority of Panda users, including most of us, run Panda with no threads. The next level is what we call simple threads. This is how we compile Panda for distribution on Pirates. And we may do other games this way too. This is not true threading. We're not actually using operating system threads. We're just faking the whole thing by playing around with the low-level CPU registers. Every once in a while, there's some code in Panda that will grab the CPU registers, save them away, including the stack pointer, and load up a new set of CPU registers and start executing there. The whole effect is that you stop executing one section of code right in the middle of that code, and you start executing another section of code. And then every once in a while, there's a section of Panda that goes and manages it, switches it back again. So Panda is really just managing this code routine switching. And it all happens in user space and has nothing to do with the operating system. This has a major disadvantage in that if you happen to have multiple CPUs, too bad, you're still using one of them. But it has a major advantage in that it's almost as fast as not having threads at all. And also, it's almost as safe as not having threads at all, because we don't really have to use mutexes and other synchronization primitives, because it's all cooperative. We only switch when we tell it to switch. There's one more option that we have here, which is simple threads, no mutex. And this means, so when you compile with simple threads, it compiles in a special mode where mutex is turned into a simple int variable, and it just flips the int variable and decides whether that's locked or unlocked. If you say no mutex, then the mutexes get compiled out altogether. There's not even an int in your structure. The main advantage to that is it takes a tiny bit less space. And trust me, on Pirates, we needed every single byte. So that's why we put that in there. Another minor disadvantage to this is that when you have mutexes, or even fake mutexes with simple threads, then it's possible for Panda to switch the context out even when you lock the mutex, which gives it more opportunities to switch contexts. If you take out the mutexes, it can't do that except an explicit called the yield, which means it can only switch context a little less frequently. So your threads might suffer from starvation a little bit more. It depends on how much you want to use your threads. And finally, we have full threads option. When we compile Panda this way, it turns all the threading primitives into actual calls into the OS. So when you create a thread, you're actually creating an OS thread. You create a mutex, you're creating an OS mutex. It's going down to the bottom. You're actually getting full use of your multi-core CPU now, and you have all the risk that comes along with it. It also slows down the whole thing considerably on a single CPU. I estimate it's about 10%, somewhere in that range. There's one more option on the very bottom, which is pipelining. There is an advanced feature within Panda that I'll get to in a little bit, in which we turn on a special pipeline render mode, in which we're doing all sorts of crazy things when we render, to render lots of things at the same time. This creates some threads automatically deep inside the IG loop in Panda, and it also changes the way that a lot of the data structures internally to Panda are set out. This, when you turn this on, adds some significant overhead, even further above the full thread option. But the potential there is to get a easy frame rate boost with a multi-core CPU without having to add any special code in your Python code. This part is still highly experimental, doesn't even work right. But this is a pipe dream right now. Ha ha. Let's see. When you have simple threads, and particularly no mutex, there's a few things that you might want to do that you can still take advantage of. Well, with any of these, actually, with any compilation mode, you have certain Panda structures that you can use. First, you don't want to use Python threading. If you try to use it, you're going to cause problems, because particularly simple threads is going to completely get broken if you have simple threads turned on and you start creating any OS calls. Now, you can create an OS system thread call as long as you promise never ever to import any Python or Panda structures into that thread. But as soon as you make the smallest Panda call inside your thread operation, you're in danger of corrupting the stack, because remember, Panda's down there mucking around with all the stack pointers. So when you're running Panda, you're probably best off avoiding all the Python threading libraries directly. But fortunately, Panda provides its own. You can just, in Panda modules, you've got this class called Python thread, which is very similar to very similar to Python's standard thread class. So if you import thread, it's very much like what you get from Python thread. You can give it a Python function to start with. You can call start. It works just the same way. And you've also got classes like mutex and condition bar, which are useful for synchronization primitives. And these are very similar also to the structures that you get when you import threading library in Python. But the advantage is that these are compiled to be whichever Panda uses. So even if you're using simple threading model or a full threading model or no threads at all, these all do the right thing. If you create a Python thread in the no threading model, it'll yell at you. But you can create one and it won't do anything. But you can ask it whether it will do anything, and then you can write special code that will do the right thing otherwise. And if you create a Python thread in the simple threads model, it'll be as if you've got a regular thread as far as you can tell. It's just running on one CPU. But import thread or import threading, bad. There are other things you can do from the Python level without really having to create explicit threads or dealing with mutexes. Just by having this stuff turned on in Panda, we have a few features built in that Panda can immediately take advantage of. In particular, you can load models asynchronously. We've had this for a while. You can say load model. We all know about load model. You give it your file name here. There's an optional parameter you can specify a callback and give it some Python functor. If you use this, then you're asking for just a asynchronous load. And this will work no matter how you compile Panda. What it will do is instead of returning a model, it returns some handle. This handle is not a model, but it's a handle that you can use to query the loader later to see if your model has come in. But when your model does come in, whether you save your handle or not, it'll call your callback function and pass it that model. And there are other tricks you can do, other variants on load model. You can load a bunch of models all at once and have your callback called when they all get loaded. Anyway, the whole point is that this will just go off and load the disk, hit the disk, read your model in, do everything it needs to do, and eventually, sometime in the future, you'll get your model. Meantime, you can go ahead and write Python code that's doing other stuff. So in theory, you're not really slowing up your frame rate. You can render it at normal frame speed. Let's see. Yeah, there's one super sneaky thing. We're not actually using this in any of our games right now, but we are using vertex paging. This is an important feature that we take advantage of pirates, and this is the entire reason that we have simple threads in Panda, so we can do this in pirates. When you have lots and lots of vertices in a complex game, those vertices take up a lot of data, a lot of memory. And on a low memory machine, you need to be able to get rid of those. Now, you could just rely on the operating system, because the operating system is good on this. If your application starts to exceed your available memory, it's going to automatically page your memory out to disk that you're not using, and when you suddenly start to use it, it's going to read it back in. Downside is that stops your whole application. In fact, it stops the whole PC while you're doing that. And you can't do anything, and the application just starts to slow down, feels really chuggy. So instead of letting the operating system page out the vertices, we've got some code in Panda that will do this magic vertex paging. And it pretty much works behind the scenes. Panda can just collect the vertices into pages automatically. It moves them down with the LU algorithm. And when you haven't used any particular table of vertices in a while, it automatically writes them out to disk. If you then come around the corner and suddenly you need to render these vertices, well, it'll load them back up for you. And this all happens with one of these threading models, according to how you compile Panda. And it works just fine in simple threading mode, which is why we're taking advantage of that. And it's pretty much automatic. You just turn it on. And there's a few config variables you can use to turn it on. And I don't know off the top of my head what they are, but you can certainly find them by looking in the code. It's good enough to know that this exists. So, high-level interface to Panda threads. Pretty straightforward, right? Threads are threads. Anything more than this you want to do, you have to do it yourself with this kind of construct. But then we're besides you should you run into race conditions. We've had some other ideas for things we'd like to do with Panda. The one key thing we'd like to do is, at some point, thread the whole task manager. Right now, the task manager in Showbase is all single-threaded. It's all very stupid. You just get a linear list of tasks, and I'll draw them like this. So every time we call task manager.add task, it's going to add something onto this list. And it's a sorted list by number. We all remember adding as a task priority, and I think it goes from smallest number to highest number. And every frame, the task manager just walks through the list, pulls the next task off the list, and runs it. And then when it reaches the end, it goes back and does the whole thing again. That's great. It's pretty simple, straightforward, does what it needs to do. One of the tasks in here is igloop, which is the renderer task. And that's typically a big, fat task. Let me draw that really big. And then you've got other things like moving your characters around, applying physics, moving this guy, doing all the things that you want to do in the game. And then you got igloop that just sits there and churns for a long time, and then your other tasks run for a little bit. And then igloop turns for a long time, and your other tasks run for a little bit. It sure would be swell if we could abstract out the things that are more important to be done every frame, and put those in a separate list all of themselves, like the one that includes igloop. You really don't want to drop igloop if you can avoid it. And then there are other things that you don't necessarily need to be done right away. Like, for instance, rotating this guy, the time of day change. That needs to be done, that doesn't have to be done every frame. Other things like calculating character animation, kind of important. You certainly don't want to lose that too long, but you can go maybe with a frame or two without doing that. So it'd be nice to have several tiers of task lists of various priority, and have a threaded task manager that's running each one of these in its own little Python thread, and can pull the tasks off the list and execute them in order, just like it's doing now, but now it can do them all in parallel. That's a pie in the sky. It's not too far off, because it's really not too different from what we've got now. The main difference is that we'd have to have an interface to the task manager to say which kind of task you'd like to add this as. And there are some other issues too. We have to make sure that we don't accidentally starve any of these tasks lists. Like I said, for instance, although character animation isn't that important, you do want it to be done at least every couple of frames. So there should be some way to rank the whole priority of all this. Okay, that's all for the easy stuff. Any thoughts, questions, comments so far? Am I going about the right pace? Nobody's asleep yet, that's a good sign. Okay. Now the magic we want to do one day is with the pipelining, and that's what I alluded to once before. Right now, most of Panda, as we think of it, happens down in igloop. There's a lot of stuff that's Python stuff, and there are a lot of functions that Python calls, or Panda functions that do various tasks, but the bulk of what Panda does is render stuff. And that's happening in igloop. And basically, igloop right now is just a function, as far as we're concerned in Python. We call it igloop, it goes and does a bunch of stuff, and when it comes back, the frame has been rendered. But it takes a long time to do all that stuff. In fact, we can divide the task that igloop does into at least two phases. And we call this cull and draw. And the idea here is that cull is everything that does not require communication with the graphics card, and draw is everything else. Cull is a little misleading. People see the name cull and assume it means view from culling, and that's part of it. But it does a lot more than that. It's also just walking through the whole scene graph, collecting the bounding volumes, aggregating the state, animating characters, basically doing everything on the CPU that needs to be done before we can start sending graphics cards to the or graphics commands to the graphics card. When it's done with all that, then it stops what it's doing and immediately starts sending commands to the graphics card as fast as it can. So the whole point of cull is to build up this list of graphics commands, and then draw starts executing. Now we made an effort to design Panda so that it does in this two-step process. Instead of simply walking the scene graph and starting to render things as soon as we discover them, we intentionally queue them up so that we can send them all at once in a batch. And the reason we do this is so that we can pipeline this whole process. In principle, once we started sending things to the graphics card, we can start working at the next frame at the same time in a separate thread. So if we're rendering frame 1 over here, frame 1, I say I'm writing 0. We're into frame 1 over here. First we cull the frame, that is we boil the whole scene down into everything that needs to be done to send to the graphics card. And then, at the same time we start sending that to the graphics card, we then immediately start on another thread culling frame 2. This is brilliant, isn't it? Because we get down to frame 3, and look at that. Actually, let me draw this up here on the other thread. I'm not sure which is clearer, but basically we can now pass a frame, every frame in half the time that we used to take, assuming the cull and draw are about the same amount of time. While we're drawing one frame, we're culling the next frame, and so on. And so we only spend half as much time rendering each frame. We're doing the whole thing in parallel. Now we're actually taking advantage of 2 CPUs. Isn't this great? We got both our CPUs working at 100%, and the graphics card is cranking away, and we've improved our frame rate. There's a few implications with this, which cause some make the whole thing more difficult than it ought to be, but just making notes on the whiteboard. But let me put that aside for now and add one more fancy feature to this. There's one thing I left off this list, which is all the Python code. Python code is also separate from all this stuff, and we call that app. So if we draw the whole thing, let me erase all this other stuff. Yeah. So remember in the big picture, we had the whole timeline up here, which is Task Manager, and in the middle of this thing was IG loop. If you imagine IG loop is broken into cull and draw, then everything outside of IG loop is app. This is everything that happens outside of the call into IG loop. Everything that's outside of Panda's domain. It's just whatever you're doing to make the game run. We don't know. We don't care. We just call it app. And this typically includes collisions. It includes all your Python code. It includes logic, moving a sky around, things like that. And now we can pipeline all 3 of these together in the same sort of way. So we have @callDraw going on the first frame, and then we have @callDraw the second frame, and @callDraw the third frame. And then it starts over again. So once the pipeline gets filled up, now we're, in theory, we're rendering 3 times as fast as we used to. And wow, aren't we great? So this is slow. I mean, this is the one of the goals of Panda, and we can't claim to have originated this idea. I mean, graphics engines have been doing this for a long time. In particular, Performer is the one that we got these 3 names from, but hasn't been as important in PC-based graphics engines recently, until recently. Fortunately, we designed Panda with this idea from the beginning, so it should theoretically be very easy for us to get there. Unfortunately, there is a lot still that needs to be done. The problem that we need to address more carefully is that when you have these three things going on in parallel, you've got 3 different copies of the same scene. You've got frame 1, frame 2, and frame 3. And these might be different. In fact, they should be different. They're running the same frame over and over. What's the point of that? Now we've got a problem. How are we going to keep this entire scene graph in 3 different copies? And how are we going to quickly copy the entire scene graph into the next frame so that we can quickly copy from the frame that app is working on to the frame that cull is working on, and so on? I mean, there's a lot of answers to this. We could make a complete duplicate of the scene graph every frame. Obviously, that would take a while. The way we tried to solve it in Panda was we introduced a structure within almost every Panda object called the cycle data. So for instance, take a Panda node. It's got lots of stuff in it. It's got its name. It's got some various properties depending on the kind of node it is. It's got its list of parents. It's got its list of children. Most of those things, with the exception of the things let's say some of those things. So the name, for instance, is part of the Panda node. on an LOD node, the switch distances, that's part of the Panda node itself. But things that are important to maintain within the pipeline that have to be different between different copies of the scene graph are stored in the object in a separate object called cycle data. And this includes the list of parents, the list of children, the transform, the state attributes on the node. Anything that you might change on a node and expect that change to immediately apply to this frame and not to any other frame have to be stored in the cycle data. And when we compile Panda without pipelining enabled, with any of the threading models but with no pipelining, this cycle data actually is part of the Panda node. And it's all one big structure. And it's very efficient to access. But when we compile with pipelining turned on, the cycle data is actually stored separately, and there's a reference pointer to it. And this is pretty easy now, because most of the time, most of the structures in the scene don't change from one frame to the next. So for the vast majority of the scene, we just keep the same object from one frame to the next, and it works perfectly. When we do happen to change an object, we have to note that the cycle data has been changed, store both the old and the new cycle data somewhere, and we have a pointer to the two copies of the cycle data. So in fact, if we have threaded pipelining enabled, then this is 3 pointers in a row. Pointer for the cycle data on frame 0, frame 1, and frame 2. But it's not so bad, because now we have to just rotate the pointers anytime we cycle the frame. And this seems to work pretty well. Of course, we've got maybe thousands of objects in Panda. We've got all of your nodes, all of your textures. Gosh, only knows. Fortunately, there are other things in Panda that don't require cycling. By Panda's design, the transform state objects and the render state objects are const, which helps because means we don't have to cycle data of those independently. And those things change a lot. The only thing that changes when we change the state is a pointer within the node. And that pointer is stored here, so we just have to cycle the pointer. So this works. This code actually exists in Panda. It works today. You can compile it, and you can run on 3 different CPUs, taking advantage of all 3 CPUs. You can see your CPU's clock at 100%. Sadly, you don't get 3x performance. Don't get 2x performance. I managed to get 0.1x performance. Well, 1.1x performance on a good day. So we've got some issues still, and we haven't quite resolved them. One guess is that maybe the extra layer of indirection is causing too much overhead. It's possible. Maybe the fact that we've got all these little objects scattered willy-nilly all throughout the heap is causing cache busting. Possible. We'll have to spend some time trying to figure out what the actual bottleneck is and re-engineer it to solve that problem. There's a few ideas we've got. Some of them are kind of kooky. But we don't need to get into that right now. But this is the dream still. Swell. Everybody follow all that?
Mm-hmm. Piece of cake.
Yeah, that's good.
So I'm volunteering to fix it.
Out of curiosity, in reality, what do your time ratios look like between app draw and cull in a production app?
Typically, they do tend to be pretty equal.
Really? Okay.
It depends on the app, but in Pirates they are pretty nearly equal.
Cool.
In Toontown, it's app dominates and cull and draw are lesser, depending on the CPU, or I mean the graphics card. And it does highly depend on the graphics card. If you're playing on an integrated graphics card, your draw is really going to dominate. There are other possibilities. In fact, Panda is configurable so that even if your app cull and draw are not strictly uniform, you can combine cull and draw to run on one CPU together, or app and cull can run on one CPU together, cool. Depending on where the balance is. And that works well, particularly on the 2 CPU machine. Oh, there's one other thing that's worth mentioning. All this stuff, all these threading compilation issues, there's also a debug mode. We can compile Panda where it turns on all these threading options, and this is even available without threads at all. But basically, it's just adding sanity checks. It does deadlock detection. It simulates the pipeline just to make sure that you're exercising all this stuff. And I've been using that fairly heavily when I was developing all this. But of course, it slows everything down considerably. Okay. There's only one more thing that's worth touching on with this whole pipelining system. There is also a grand scheme one day to have a kind of distributed rendering feature of Panda. This whole system is a process by which we distribute the Panda rendering onto multiple CPUs within the same box. Ultimately, we'd like to be able to render the application on multiple boxes. So you have your app Python would be running on just one box, and it would be sending the scene graph, distributing the scene graph to remote boxes, probably using a mechanism very similar to the pipeline cycler. Since we've got the pipeline cycler, and it knows whenever it gets touched, we could attach a callback onto there that every time the pipeline cycler gets touched, it automatically sends its data, its new data, over to the remote PC, who integrates it and updates it. So you could have col and jar running on a remote PC and app running on your home PC. That way you could have multiple different PCs all running different views of the same scene. And that would be pretty spiffy. But that's completely theoretical at this point. But the reason I bring it up is because it does touch into the whole pipeline system. Okay. I think that's all I got to talk about for threads.
What are some applications you're looking at for that last one out of curiosity? It seems like it'd be good for like a VRML type application where you've got a scene with a lot of different viewpoints where not a lot of stuff is changing. I'm curious about what else you've got in mind though.
Well, it's actually pretty good even for scenes where a lot of things are changing, because that's the whole advantage of the distribution. Because your app, as your app is changing, it's automatically changing remotely. The big push for that is the work that WDI is doing.
Mm-hmm.
Mark Monet and his group have much need for distributed rendering, for rendering filling big render screens, cave-based stuff. Midway Mania is a good example of this. I don't know if you know about the Shell Games project, but they would have been happy to take advantage of that feature had we been able to put it right.
Okay.
Instead, they had to be able to cram everything down into one CPU.
Right. So you're just looking at an efficient way to get the same scene to a ton of displays.
Yes.
Basically what it comes
Yes.
down to. Okay. Cool.
And I mean, one great example would be a video wall, for instance.
Yes.
Where you have just each display is just a tiny little segment of the scene. You can have a really complex scene and put a really kicking graphics card in each box, and boy, that's parallel.
Cool.
How about like Pirates TV or something like that? Some kind of thing where you could watch the world from someplace else.
Ghost View.
Yeah.
Oh yeah.
Spectator
yeah,
mode
sure.
or something.
That sounds well. That'd be kind of fun. Let's do that.
Have you considered stackless Python for the threading stuff?
I know almost nothing about stackless Python. Does it help threading?
I know it's just something about cooperative execution. That's about it, as far as I know.
It is true that traditional Python gets a lot of guff for not being threaded. Python's biggest weakness is that it doesn't do threads very well. Because the whole Python interpreter really wants to be single-threaded. And if you have multiple Python threads, they really just take turns, even if you've got multiple CPUs. Maybe stackless Python is designed to deal with that. I don't know. But most of the threads I'm talking about at the low level are down inside C++ and don't really affect Python that much.
I think stackless is still limited in one process.
Is there?
I don't think it's, or I mean one core.
One CPU? Yeah.
I don't think it's mainly just a way to do ultra lightweight threads.
Okay.
Or ultra lightweight fake thread things.
Similar to our simple threads?
Yeah, I don't think it goes beyond changing the way. I don't think it gets rid of the global Python lock that everybody hates.
Okay. Great. Thanks for coming. See you next week.
What's next week's topic?
TBD. Turn that on.